Welcome to the Explainer. Today, we're going to treat algebraic equations not as some confusing jumble of numbers and letters, but as satisfying, completely solvable puzzles just waiting to be reverse engineered. If you've ever stared at a massive math problem and felt entirely lost, well, you're about to get a whole new perspective. Because we really have to ask ourselves, what happens when you need to put the algebraic toothpaste back in the tube? You know, it's relatively easy to multiply things together. You just distribute and combine. But what on earth do you do when you're staring at a massive, complicated equation and you need to break it back down into its fundamental building blocks? Okay, let's dive into this by thinking of math a lot like Lego. If algebraic expansion, or multiplying terms, is like snapping pieces together to build a solid wall, then factorising is the exact opposite. Factorising is carefully, methodically dismantling that wall back down into its original, individual, distinct bricks. So, the absolutely crucial point here is that our primary objective today is to find these factors. Factorization is literally just the process of writing an expression in the form of terms or brackets multiplied together. We want to find the pure, unbroken pieces that make up the whole polynomial. Here's our 6-step roadmap for today. 1. Reverse engineering algebraic equations. 2. The common factor tool. 3. The art of grouping. 4. Cracking the trinomial code. 5. Mastering squares and cubes. And finally, 6. Algebra in the real world. Section 1. Reverse engineering algebraic equations. Before we start ripping equations apart, let's establish exactly what we're trying to achieve when we look at these classic textbook problems. It sounds brilliantly simple when you say it out loud. Factorization is the exact reverse of multiplication. Keeping this golden rule actively in your mind is going to anchor absolutely everything else we do today. We aren't creating new math, we are literally just hitting the rewind button on multiplication. Section 2. The common factor tool. All right, let's grab the very first and easily the most reliable tool in our kit, the common factor extractor. This is always your starting point. Whenever you face a new expression, run through this simple 3-step procedure first to see what easily pulls out of the entire equation. Step 1. Find the highest common factor, or HCF, of all the terms. Step 2. Divide each term by this factor. And Step 3. Enclose what's left within brackets, leaving that common factor parked right outside. What's really interesting here is how visually satisfying this is in practice. Take a look at the expression 6a squared minus 3ax. The highest common factor there is 3a. By pulling that 3a out to the front, you instantly simplify the equation, and you're neatly left with 2a minus x safely tucked inside the brackets. It cleans up beautifully. Section 3. The art of grouping. But wait, what happens if you scan an equation and there just isn't a single common factor for the whole thing? What if you have an even number of terms, say 4, and no single piece perfectly divides into all of them at once? That is exactly where tool number 2 comes in, grouping. The strategy here is divide and conquer. You temporarily split the equation into smaller teams that do share a common factor. You factorize those smaller teams, and suddenly, like magic, a new, larger pattern emerges. This perfectly illustrates that method. Looking at a 4-term polynomial, by grouping the terms into pairs and pulling out the common factors from just those smaller pairs, it magically creates matching brackets. We can then extract that entire matching bracket as a whole new Lego block. We literally just turned a messy 4-term polynomial into 2 neat little brackets. Section 4. Cracking the trinomial code. Okay, time for tool number 3, the trinomial splitter. This one's for when you're staring down those classic, often intimidating equations that have 3 terms, usually starting with an x squared. You know the ones, ax squared plus bx plus c. The secret trick here is realizing that a trinomial is really just a 4-term grouping problem wearing a disguise. You just have to split that middle b term into 2 specific parts first. Once you have 4 terms, you just use the exact grouping tool we just learned. Let's see how this builds in practice. Take x squared plus 5x plus 6. We need to split that middle 5x. Since 3 plus 2 equals 5, and 3 times 2 equals our n number 6, we split it into 3x and 2x. Suddenly, we've got a clean 4-part puzzle. X squared plus 3x plus 2x plus 6. From there, just group them, pull out the common factors, and you arrive right at your answer, x plus 3 times x plus 2. But before you waste 10 minutes trying to crack what might be an impossible code, there's a quick cheat code to test if a trinomial is solvable in the first place. Check the coefficients using the formula b squared minus 4ac.
If your result is a perfect square, like 16, 25, or 100, you know for an absolute fact it can be factorized.
For instance, let's say we want to know if 5x squared plus 17x plus 6 is factorizable. We quickly plug the numbers into our cheat code, 17 squared minus 4 times 5 times 6. The math gives us 169. Since 169 is a perfect square, it's 13 times 13, we immediately know it's worth our time to solve. Section 5, Mastering Squares and Cubes. Incredible. Now, our final set of tools are what I like to call the specialized keys. These aren't for everyday equations. These are meant for very specific locks, perfect squares and perfect cubes. Lock this formula into your memory right now. The difference of two squares. It states that a squared minus b squared equals a plus b multiplied by a minus b. Whenever you see two perfect squares with a minus sign trapped between them, they will always pop apart perfectly into these twin brackets. No exceptions. And you can see how powerful this specific tool is. Even an expression as scary looking as 16a to the power of 4 minus b to the power of 4 instantly breaks down. Just view it through the lens of our squared formula tool, turning it into 4a squared squared minus b squared squared, and it just cascades down into perfectly neat factors. We also have formulas for the sum and difference of cubes. And yeah, they certainly look a bit longer and more complex, but they behave in the exact same way. They act as a master key. If you spot an a cubed plus a b cubed, you don't need to guess. You just plug it straight into the expansion formula, and the puzzle practically solves itself.
Section 6, Algebra in the Real World.
So we've gone over the tools, but why does mastering this Codebreakers toolkit actually matter outside of just passing your algebra exam? Why go through all the effort of pulling these mathematical Lego bricks apart? Because factorization is exactly how we model and solve complex real-world systems. Take this case study. A government allocated massive welfare funds for refugees, and the total fund is mathematically modeled by the polynomial x to the power of 4 plus x squared plus 1. To figure out the equitable amount each individual family receives, they have to use factorization to break that giant expression down into workable pieces. Math isn't just on the page, it's distributing resources.
Which is why I want to leave you with this final thought to ponder. We've seen how factorization reverse engineers math equations, but how does this invisible math quietly govern the logic of resource distribution and problem solving around you every single day? As you step back out into the world, ask yourself, what other massive, overwhelming problems are just waiting to be systematically broken down into manageable pieces? Thanks for joining me on this explainer. Keep looking for those underlying factors, and I'll catch you in the next one.